video, we will be talking about one of the most important types of graphs. That is the graph of a polynomial function. Let's begin. Recall that a polynomial function can be written in expanded form, where we have our highest degree term at the beginning and our smallest degree term, the constant term, at the end. Sometimes that can look confusing to students when it's written this way: f of x equals a sub n, x to the nth power. Then notice that we are decreasing each time. We go down by 1 power until we get to our constant term here, a sub 0. So we notice that is our constant term, right? We call this a polynomial function of degree n, where n is our highest power, as long as all exponents are whole numbers. Remember, whole numbers are your natural numbers, 1, 2, 3, going on forever, as well as 0 itself. So as long as we have whole numbers for each of our exponents, we have a polynomial expanded form function. We have special names for pieces of the function, like leading coefficient, which is just our coefficient of our leading term, meaning the term with the highest power. We also have the leading term itself, which is our term with our highest power, and of course the constant term, which has technically an exponent of 0, which you don't really see. X to the 0 power would just be 1. So one of the reasons that we would like to focus on polynomial graphs in this chapter is because their graphs are continuous, meaning that we can draw them from left to right without ever picking up our pen. In other words, we could say in our first bullet point that graphs of polynomials are continuous. From negative infinity to positive infinity, and you can see that in interval notation with those parentheses, meaning that there is no break or no hole in the graph. Now that's not always the case with our functions that we've studied in previous chapters, and in future chapters we will be reviewing rational functions where we have holes sometimes, or removable discontinuities, or just breaks in the graph called vertical asymptotes. But with a polynomial graph, that doesn't happen. Also, polynomials, by looking at the degree, the highest power, we're able to know immediately how many real zeros we have. Remember, real zeros, those are the x values, which if you replaced x with those numbers, you would get 0 for your y value. So what input would give you an output of 0? Those are what we mean by real zeros, or x-intercepts. So if we know the degree is, let's say, 4, we are guaranteed to have up to 4 x-intercepts, no more. Similarly, by knowing the degree, we know how many times that polynomial's graph could turn around, right? So if I have a degree 5 polynomial, it turns out that I could have up to, but no more than, 4 turns. In other words, the degree minus 1, or n minus 1, is the number of turning points that we could have potentially, up to. Let's take a look at an example of this. If f of x were y equals negative 4x to the third power plus 5x to the second power minus 7x plus 3, this would be an example of a polynomial whose degree is 3. So thus we can say that we know it has a maximum, or at most, 3 real zeros, 3 x-intercepts. It also has a maximum of 3 minus 1, or 2 turning points. A couple of other fun facts about polynomials. These 2 bullet points actually together make up what we call the factor theorem, which I'll be referring to in future lessons. This factor theorem says that if you have a 0, so again, what is a 0? A location for x, a value for x, an input for x, which would result in zeroing out your y value, your output. So if you have a 0 that you know about, let's call it c, some number. If that's a 0 of the polynomial f, then we are guaranteed to have a factor of the polynomial f. And that factor would be of the form x minus c. Now, if that doesn't seem to make a whole lot of sense yet, that's okay. Let's go the other way. If we have a factor, x minus c, of a polynomial, then that means that that factor times some other factor would give us our polynomial in expanded form when we FOIL it out. Now, the reason that this direction is true is that if we were to try to find the zeros of the polynomial, we would set our y value equal to 0. And remember that if something times something is equal to 0, The zero product rule says that the only way that could happen is if the number itself was equal to our 0. So we would take our x minus c, for example, setting it equal to 0. That would mean that x would have to equal c, which gives us the second part of the factor theorem, that if x minus c is a factor, we know that c is a 0 of the function. Now, you've actually done this before. In previous math classes, when you were dealing with your parabolas that opened up or opened down, when you were trying to find your x-intercepts for those parabolas, sometimes we had none, sometimes we had 1, other times we had 2. But the way we would go about finding those, the hunt for our x-intercepts, was by first setting the polynomial equal to 0, and then factoring, or using the quadratic formula, the square root property, or completing the square to solve for those x-intercepts. Let's take a look at an easy one. Suppose we have f of x is equal to x squared plus 5x plus 6. In that degree 2 polynomial, so we're guaranteed again to have up to 2 real zeros and 1 term by the degree. In that polynomial, we would know that actually factors, doesn't it? What factors of positive 6 with the same sign add up to positive 5x? Well, that's x plus 2 and x plus 3. With that information, we can now see that by setting that equal to 0, we would have our real zeros of negative 2 and negative 3. And so now we can see that that factor theorem does apply here. When I have a factor, x plus 2, I end up with a real 0 of negative 2. And when I have a factor of x plus 3, I really end up with a 0 of negative 3. And this will be an important skill for us as we go forward. As we are given more complicated polynomial functions, we will want to be on the hunt for those zeros or those x-intercepts. All right, well, let's head over to our next slide together. Clear that out? All right. So another fun fact that will help us to graph these polynomials, by looking at the degree, we're able to tell one of the 4 ways that the graph will behave as you go to the left forever and to the right forever. And so what I mean by that, left forever, right forever, is something called the end behavior of our polynomial functions. So what we want to do when trying to figure out which of these 4 end behaviors we're dealing with is by first beginning to look at the degree. So let's switch colors here because I got a little bit bored with that color blue. How about red? Okay, so let's take a look at our degree. If our degree of our polynomial is even, what that's telling me is that at the ends, as I go to the left forever, my graph will also go up forever, and if I go to the right forever, my graph will also go up forever. So they behave the same way at the ends. They're going to go in the same directions at the ends. On the other hand, so this was same direction, if our degree is odd, that would mean that at the ends, as we go to the left forever or as we go to the right forever, our y values will go in opposite directions, either increasing from left to right or decreasing from left to right. So one of those 2 scenarios will happen. So if it's an odd degree polynomial, we're going to go in different directions at the ends. Now, why is it so important to know what's happening at the ends of our graph for a polynomial function? Because we mentioned earlier that for a polynomial's graph, they will be continuous forever, left to right, which means once we know what happens at the ends, and we know that it's continuous in between those ends, all we'll have left to do is find our x-intercepts and y-intercepts, and we have a sketch. So that's the goal. End behavior is a great place to start. So let's take a look at an example of this. We're given f of x equals negative 4x to the 3rd power plus 5x to the 2nd power minus 7x plus 3. In this expanded polynomial function, we can see the degree by simply looking at the highest power. The degree here happens to be 3. So if I have an odd degree, so my degree is odd, and I have a leading coefficient, so the sign is important, of negative 4, so my sign of my leading coefficient, I'll use LC if you don't mind, for leading coefficient, is negative. It's a negative 4. Since I have a negative leading coefficient along with an odd degree polynomial, I know that at the ends, my graph is going to go in opposite directions. If you look at the chart here that's been provided for you on the slide, you see that whenever we have odd degree, we have the situation where we're either increasing from left to right or we're decreasing from left to right based on the sign of the leading coefficient. Since ours is negative in this case, we know that our end behavior for this polynomial with degree 3 and negative leading coefficient, -4, would be something like this, where as we go to the left forever, we're going up forever, and as we go to the right forever, we're going down forever. You can click on the Desmos link on your own, which is on the slide, and you'll see the actual graph, and it will go according to what we have on our screen here. The end behavior will be decreasing from left to right. Notice, though, as you go on further and further in math, we prefer to write in terms of what we call limit notation. And so the way I would describe this end behavior visually is just like we've already done, where we're indicating that we're going to be decreasing from left to right. But formally, we would say, as x approaches negative infinity, which means as my x values get more and more negative, so smaller and smaller x values, my y values, f of x, are approaching what? Well, as your x values get further and further to the left, and you can see that in our picture here, as your x values go further and further left, our y values are going up and up and up and up and up forever. So our y values would be approaching positive infinity, wouldn't they? Similarly, the second part of our end behavior formally would be to say, what's happening as x approaches positive infinity? Well, we can see here that as x approaches positive infinity, our graph is going down, isn't it? So we would have f of x approaching negative infinity. So that would technically be, I'll put it in quotes here for you, the formal way of writing our end behavior here. As x approaches negative infinity, f of x approaches positive infinity. But as x approaches positive infinity, f of x approaches negative infinity. If that seems a little uncomfortable for you right now, it's okay. It's brand new. That makes sense. What you'll want to do is when you're doing your homework and you're practicing, in addition to sketching it out like we did up here of what it's going to look like, make yourself get in the habit of writing out formally the end behavior so you feel more comfortable as you move forward, because that's how we'll refer to it going forward. Okay, well, let's start practicing, putting this into practice now. We've talked about degree, we've talked about end behavior. Now we're going to put this together with x-intercepts so that we can start getting graphs of our polynomials. So let's head over to our next slide here. Okay. So in our next slide here, we're going to actually practice putting this all together. Here, though, we begin with a polynomial in our example that is not in expanded form, but rather it's in nice, compact, factored form. So we take a look and we have something like f of x equals 5, our leading coefficient, turns out to be a 5 here, times a parentheses where we have x plus 2 to the second power. What does that mean? Well, it means that you have a factor that goes in 2 times into this function, right? So you have a factor that goes in twice evenly. We'll talk more about that in our future lessons reviewing division, right? But right now, that's what it means. It's been repeated. We have a fancy name for that, and that's called the multiplicity of a factor. So the multiplicity of a factor is going to be the actual exponent of each factor, okay? Now, we have another factor here that has a different multiplicity. So for the factor x plus 2, I would say that that factor has a multiplicity of 2, which is even. And that will be important for us in a minute. But the factor x minus 3, on the other hand, has a multiplicity of 1. It only appears one time. It goes into the function evenly once. So I would say that this one has a multiplicity that's implied. If you want to write the 1 there, feel free. That might help you understand more visually what's going on. So what happens here? Well, it turns out that if you just keep in mind a couple of pieces of information from your previous knowledge, they'll really help you right here. For example, what I like to keep in mind is the graph of y equals x squared. I keep that in my head. The graph of y equals x squared is a polynomial that's very simple. Remember our 3 key points there? 0, 0, because 0 squared is 0. 1, 1, because 1 squared is 1. Negative 1, positive 1, because squaring negative 1 gives us the y value still, the output of 1. And again, it will continue to grow. 2 becomes 4, etc. And it looks something like that, a parabola opening up with some nice symmetry. The reason I bring that up to us to remind ourselves of that graph is because we actually do have some information about a 0 here. we have a 0. Let me switch colors so it can be more clear for you. We have a 0 here at the origin, don't we? That would be our x-intercept, if you will. And at that 0, what happened? Well, we touched the graph on the x-axis, and then we turned around. I'm going to write T for touch, if you don't mind. So in that situation, we touched at the x-axis, and we turned around. And that should make sense, because if you're squaring x values, they're becoming positive, aren't they? So you can never actually dip below the x-axis and become negative. So that brings us to an interesting point. The x-intercept for that graph was 0. So in other words, I could have been writing this as x minus 0 getting squared. Now that might look really strange to some of you, but remember the factor theorem that said if c is a 0, then x minus c is a factor? Right, so that's what happened here. If 0 is a 0 of the function, then x minus 0 is a factor, which is saying here that this factor, if it's truly going to touch and turn around, its multiplicity must be even. And that brings us to fill in our first blank here for our bullet points. If the multiplicity of a factor is even, which we just saw happen, in that situation, at that x-intercept, which is associated with its factor by the factor theorem, then the graph should simply touch and turn around. Another way of saying that is bounce off. Either way, I would understand what you're saying at the x-axis at that location. On the other hand, though, let's remind ourselves of another important graph that will help clarify what's going on, hopefully. Y equals x to the third power. So if I was graphing y equals x to the third power, keep in mind what that would mean. We would have 3 points again, 3 easy points anyway. There's lots of points in this graph. But at 0, 0 cubed is 0. 1 cubed is still 1 for our output. And negative 1, cubing a negative, you'll get a negative 1 as a result. So that would actually give you those 3 points at -1, -1, 0, 0, and 1, 1. Of course, there's more points than this. This is not a line, because if you were to put a 2 in there, for example, 2 to the third power, you're jumping up to 8, aren't you? So that would jump right up. And similarly, -2 would jump up to -8. So something like this is happening. We have our snake graph, so one of our basic functions again. Again, why am I bringing this up? Well, let me switch colors so you can see clearly what I'm trying to say. Here we have an x-intercept at 0 again. But look at what's happening this time to our x-intercept. Instead of touching and turning around at 0, we're actually crossing. I'll put C for crossing if you can see that. So what do we have here? Well, we have the situation that when we have, again, a 0 at 0, that's x minus 0 to the third power. What we really are saying is that if the multiplicity is odd, we're going to have to cross through the axis. And why is that? Well, because when you go to the right of it, you're going to have a positive, and when you go to the left of it, a negative. You're going to end up having different signs, which is why you're crossing the axis. That brings us to our second fill in the blank up here. If the multiplicity of our factor is odd, then the graph must be crossing or cutting through the x-axis at that location. Okay, putting all of this together, now that you have completed notes, let's see if we can answer the question. If I were giving you a function like this, f of x is equal to 5 parentheses x plus 2 to the second power times x minus 3, could you begin the process of getting yourself ready to graph this by hand? That's what we're really trying to do here. Well, yeah, we could talk about the degree. We could talk about the x-intercepts and their multiplicity, and together we'd have enough information to start sketching our graph. So let's take a look at what we know. We actually know the degree. Now, this is where things get a little bit interesting for students, so see if you're still tracking with me. If it was expanded out to find the degree, what did we do? That's right, we simply looked at the highest power. On the other hand, if we have them in factored form, eventually wouldn't we have to FOIL them out to get back to expanded form? Yeah, which would mean that if I took 5 times x plus 2 times x plus 2 times x minus 3 and did all of that FOILing, eventually, would you agree that the highest term would have x cubed involved? Because x squared times x is x cubed. So the degree ends up actually being 3. Now that can be confusing because a lot of people just look at the 2, the highest power, and they think the degree is 2 here. But remember, if you were to expand, you would end up adding up the 2 and the 1 to give you 3. So when finding the degree for factored form, you really add your multiplicities. So when I do that, I get 2 plus 1, or 3. Now the reason I bring that up, not only does 3 help us find our end behavior, so we're going in opposite directions at the ends, but we also would now be able to know how many real zeros we have to account for. We have up to 3 real potential zeros. Some may be repeated or not. Some may be real, some may be imaginary, but we'll have to account for all of them. In this case, for example, if I were to set y equal to 0, letting y equal 0, I could find my x-intercepts, also known as my real zeros, and they would be, if you take 5 and set it equal to 0, that's impossible, so that's not going to produce any real zeros. But if you set x plus 2 equal to 0, wouldn't that mean that x equals negative 2 would be a real 0? And if you set x minus 3 equal to 0, wouldn't that mean that x equals 3 would be a real 0? Precisely. What this is telling us now is that at those values, we have x-intercepts. If they're real numbers for your zeros, those are x-intercepts. So for this graph, if I was interested in drawing a sketch, and please feel free to check Desmos, the link is there provided for you after the video, or you could pause it at any point and check it out yourself, right? But what should happen in your sketch is you should see the following. At negative 2, we should be having a real 0. At positive 3, we should be having a real 0. So let's take a look at that. Negative 2, x-intercept. Positive 3, x-intercept. What that would mean then, if we were continuing the graph, is we would use our degree, which tells us that we're going in opposite directions at the ends because it's odd, and the leading coefficient, which is positive, so we're increasing from left to right. So we could actually start our picture just using the end behavior at each extreme or furthest away x-intercept. Now in between there, we'd use our multiplicities. So if we had a multiplicity of 2, which was even, so this had a multiplicity of 2, which is even, then that meant that at that location, we should not be crossing, but rather touching. So when we get to negative 2, we're going to touch and turn around. We're going to touch and turn around. Now you might be wondering, what about the y-axis? Do I have to hit the y-axis at some point? Well, yes, because if our graph is truly continuous, if it's a polynomial, it should be continuous left forever, right forever. So that would mean that at some point, we have to cross the y-axis. We have to have a y-intercept. So if you wanted to find a y-intercept, you could just let x equal 0. Letting x equal 0 here, we'd get 5 times 0 plus 2 is 2, and squaring 2, we get 4. 0 minus 3 is just negative 3. So what do we end up with? Well, guess what? Our y-intercept is really, really far down. It's at 20 times negative 3, or negative 60. So way down yonder somewhere at negative 60 would be our y-intercept, okay, just to have an idea of what's going on. So you might not even show that on your graph necessarily if you're in a hurry, but the idea is, yes, at some point, we will hit the y-axis and turn around. What about at the other x-intercept? Well, at the other x-intercept of 3, we had a multiplicity of 1, which was odd. And we mentioned in our bullet points above that if we have an odd multiplicity, just like with the x cubed graph here, we have to cross the x-axis, cut through the x-axis. So we are actually going to approach our x-intercept, and then we're going to cross through. Okay. So in that graph, notice what we have here. Again, this is just a sketch below, but if you were to pull up the Desmos link and go to that graph, the actual formalized graph, you would notice that you have an x-intercept at negative 2, which gets touched but not crossed, and an x-intercept of positive 3, which does get crossed, and that your end behavior was correct, that you'd be increasing from left to right. So that's pretty much what we're going to be doing for the rest of this video. We're going to be practicing how to graph polynomials when given the factored version of the graph. We may also talk about how to create our own graphs equation. So let's head over. At any point, feel free to pause and practice on your own, of course. So again, this example is just like the one we just did. So if you want to pause now, that would be a great idea. See how much of this you could do yourself. All right, here we go. Let's see how you did. We would begin by analyzing the graph, recognizing that this polynomial is in fact in factored form. It has a leading coefficient of -2. We'd also notice that it has a degree. If I were to write the degree up here, let's say, its degree would be the sum of the multiplicities. So 2 plus 1 plus 1, 2 plus 1 plus 1 is 4. And 4 is even. So at the ends, we're not going in opposite directions like the last problem, but rather the same direction, both up or both down. So we know that one of those is happening. But because it's a negative leading coefficient, it would be the case where they're both going down at the end. So for our end behavior, visually, this is what's going on. I encourage you to go back to the earlier slide where we defined end behavior and make sure you can write this correctly in limit notation as well. Let's continue. Our real zeros, if we set each factor equal to 0, x plus 3 has been repeated, but when you set x plus 3 equal to 0, you get -3. Its multiplicity is 2, its power, which is even. So at that location, our graph will simply touch, not cross. X minus 3, if you set that equal to 0, you would get x equals 3 for a x-intercept or a real zero. Its multiplicity, the power, is 1, which is odd, which meant we cross. X plus 1, its factor, if you were to set it equal to 0, would give you x equaling -1. Again, its multiplicity or power is 1, which is odd. So again, we cross. So we've already mentioned the end behavior. We have that part done. The maximum number of turns is always the degree minus 1, so n minus 1. In this case, the degree was 4, so 4 minus 1 is 3. Now, why would you want to know that? Because when you're doing your sketch, you don't want to have more than 3 places where the graph turns around. So that would be the importance there. All right, good job on that one. Let's head to our next. The next slide here, we're summarizing everything we've been talking about. So nothing really new here, but if you want a nice, organized, systematic way to graph your polynomial functions, here you go. First thing we did was we determined our end behavior. The way we did that was we looked at our degree. Was it even or odd? So am I going in the same directions or opposites at the ends? And the sign of the leading coefficient. Am I increasing or decreasing left to right? Secondly, we looked for real zeros. And if we're in factored form, it's already basically staring right at you because of our factor theorem, which said if x minus c is a factor, c is a 0, and vice versa. So finding the real zeros is really nice when we have factored form. That's not always the case. Sometimes it's expanded, and we'll have to do more digging to find those zeros. But today, this is what we'll be giving you. Behavior at zeros. That means once you find those x-intercepts, those real zeros, am I touching or am I crossing? So basically here, we're looking for our multiplicities, aren't we? Of each zero, of each factor. Finally, since every polynomial's graph is continuous from the left to the right forever, they have to cross the y-axis one time. In order to be a function, they couldn't do more than that. So we should always be able to find a y-intercept by letting x equal 0. Carefully do the arithmetic correctly and you'll get that y-intercept. It may be really, really high, really, really low, but we still can get it, no problem. Using symmetry, you can go back and read about symmetry or watch YouTube videos about symmetry, but the basic idea there is if you have a function which you know has y-axis symmetry, then once you have one side of the graph, you have the other side of the graph by that symmetry. Similarly, origin symmetry does the same thing for you. One side of the graph gives you the other side. So if you want to save time, you could always check for symmetry. So make sure you research that. It's an old skill, but we're not going to go over that in today's video. Test points. If you need them, you can always pick an x value in one area of a graph, plug it in as your input to your function's equation. It spits out an output, and that would give you an idea in that region of the graph, am I above the x-axis or am I below the x-axis? So that will you get some practice in the homework with that as well. And finally, the maximum number of turns, that was always the degree minus 1. So 1 less than your degree. Again, I like to keep in mind the graph y equals x to the second power, that nice parabola. It had 1 turn and the degree was 2. So that's a nice example of how the degree will always be at most 1 below the number of turns will always be at most 1 below the degree. Let's take a look at a nice easy example of this, and we're almost done with the video, I promise. You're always welcome to skip ahead if this is too easy though. F of x is equal to x squared minus 4x plus 4. Well, that's a degree 2 polynomial. So if I was trying to follow this step-by-step approach, I would begin by trying to determine my end behavior, right? So for my end behavior here, I would notice that my degree is 2, which is even. So if I have even degree, that meant what again? Yeah, that they're going the same direction at the ends. And then my leading coefficient was positive. So if I have a positive leading coefficient, this meant that at the ends we're both increasing, aren't we? So we know something like that is happening as our end behavior. Again, formally you could say as x goes to negative infinity, y goes toward positive infinity. And as x goes toward positive infinity, y is also going towards positive infinity. In addition to end behavior, we could find the zeros of this polynomial very easily because this one is very easy to factor. In fact, the factors of 4 with the same sign, which add up to negative 4x, would be x minus 2 and x minus 2, a repeated factor. Another way of saying that, you're probably thinking it, that's right, x minus 2 to the second power. Well, that looks familiar, doesn't it? We have a situation where our factor has a multiplicity of 2, which meant that the behavior at that 0 would be to bounce off or to turn around. So let's go to the graph. We know that our x-intercept is at at positive 2, because you have to set them equal to 0. X minus 2 equals 0. Move 2 to the other side, it becomes positive. So if we have an x-intercept at positive 2, let's see if we can show that on the graph. So far, so good. There's our x-intercept at positive 2. We would know that this graph is going to be going up because of our end behavior, left and right. We'd also know that at the x-intercept 2 itself, it's going to touch, not cross. So it's going something like that, touching and turning around. If you wanted a more comprehensive graph, you could use symmetry to get points on both sides. You could also check and see what the y-intercept is. The y-intercept here is not difficult. If you simply let x equal 0 here, you get 0 to the second power, which goes away, minus 4 times 0, which goes away, and you're left with just the constant 4, aren't you? So in this case, the y-intercept would be actually 1, 2, 3, 4 above the origin. So I could actually sketch a better graph that way, and then using the symmetry along x equals 2, when I go 2 to the right of our vertex, we're also 4 units up. And I could finish that graph off pretty nicely. So I have a decent sketch. Now you might think, I could have done that a different way. I already knew how to graph polynomials from previous classes. Great. But right now we wanted to show you how we could use the general approach to graphing polynomials in order to graph a simple one we already knew how to do a different way. Okay, last example I believe. Let's head over. Again, feel free to try it first by yourself. In example 2 here, the official example 2, it says, please sketch the graph of this polynomial function. Again, it's in factored form, but there is a little bit of a difference here. Notice here, my first term, or factor rather, is 2x to the second power. Now that's really interesting, because in the past, we would just have a number there, right? You might be thinking, I thought that was my leading coefficient. Why is there an x squared next to it? Good question. In reality, the 2, let me switch colors on us here to make it hopefully more clear for us. The 2 here, maybe we can see that better, maybe not. The 2 here is still our leading coefficient. So we have a leading coefficient of 2, which is positive, right? So that's positive. So that part's still the same as before. The unique part is what's happening with the zeros, right? So with our zeros here, we have a 0 at x minus 0 squared, right? That's really what's happening there. If you have x squared, it's really x minus 0 squared. We have another factor of x minus 2 and another factor of x plus 1, right? But if we were to say that's basically y equals that, right? 2 times that. If we were to set each of those equal to 0, wouldn't we get that x equals 0, that x equals 2, and that x equals negative 1, setting each of those factors equal to 0? Yeah, that's just the factor theorem again. The 2 is important. If you're wondering what role does the 2 play, remember that is actually stretching the actual graph at the ends because it's multiplying all of your y values by 2 at the end. So it is stretching it out, but it's not going to change the x-intercepts. It'll change the y values, but not the x-intercepts. So what does that mean for us? Well, we would know that at 0, we have an x-intercept, at 2, we have an x-intercept, and at -1. So on my graph, let's show that. At 0, x-intercept, at 2, x-intercept, and at -1, x-intercept. Now, what about the end behavior? Well, for end behavior, not only do we need the sign of the leading coefficient, but we also needed the degree. That's right. What was our degree here? Our degree would have been, remember, the sum of our multiplicities. So 2 plus 1 plus 1. And 2 plus 1 plus 1 is 4, which is even. So if we have even degree, they're going the same direction at the end, either both up or both down, right? But we have positive leading coefficient, so we're both going up. That means that together we can interpret our end behavior, can't we? With our leading coefficient and our degree being even, our leading coefficient being positive, our degree being even, that means that our end behavior should be both going up as we go left and right forever. So we've seen this one already once today with our previous example. So in this case, we would say that I know that at the ends, maybe I'll switch to blue, maybe it'll be seen, let's see. At the ends, I should be going something like this, right? And something like that. That should be happening at my ends based on my end behavior, right? What else do we know? Well, we know that at the actual x-intercepts, we are either touching or crossing, and that will be determined by the multiplicity. So take a look at the x-intercept 0. It came from a factor whose power was 2, which is even. If it has an even multiplicity, what did that mean? That's right, it touches and turns around there. On the other hand, the x-intercept 2 came from the factor x minus 2, whose power was 1, which is odd. So there we're going to cross, and at -1 for our x-intercept, its factor had a multiplicity of 1 as well, which is odd, so we cross. Putting all of this together, starting from the left, we are starting as we go down until we approach the x-intercept here. At -1, what happens? Well, we should cross, shouldn't we? So you need to show me that you've actually crossed the x-axis there. At some point, which you'll learn about in calculus actually, in calculus 1, where exactly you have your turns, but at some point we have to turn around and go up because we know that the next x-intercept has to be reached, and that is 0. What happens at 0? Well, according to this multiplicity being even, it should touch and turn around. So we're going to approach 0, touch it, and turn around. Finally, at some point in the future, again, you'll learn when that is, you're going to have to turn around again. Now, how many turns could we have had? Our maximum number of turns is the degree minus 1. The degree was 4, so 4 minus 1 is 3. So as long as you didn't show more than 3 turns, for a sketch, this is just fine. I've already showed it turning once here, twice here. This would be my 3rd turn. So at some point, we'll turn around again. We'll approach our x-intercept of 2, which is going to get crossed. So if you showed a sketch something like this, you'd get full credit because you've shown me the main pieces that I was looking for. You've shown me the correct end behavior, that you're going up as you go left and right forever. You've shown me the correct x-intercepts at 0, 2, and -1 based upon the factors and the factor theorem. Finally, using their multiplicities, you've shown me correctly whether we've crossed or touched at those x-intercepts, and you were careful not to have more turns than were allowed, which is the degree minus 1. Remember, there's always a Desmos link here, so feel free to check that out. But at this point, it's up to you to go practice and make this your own. Good luck. Remember, math is not a spectator sport. You gotta try.